Good morning, everyone. So I will present you the BIRDY CubeSat. CubeSat to a small body of a solar system. More than a CubeSat, I would say it's a concept where we are developing a few elements. And a small body means also any body of the solar system with a low gravity. And BIRDY-T, also T means for technology, because it's a long way to have an interplanetary CubeSat doing all the science we want on these bodies, and we will start with technological development. We are having at the Pascal Research University in France, in collaboration with colleagues from NCKU, Taiwan, and also from Odysseus Space LTE, space in Taiwan. So when I say small bodies, it's low gravity small bodies. It can be asteroids, of course, like near-Earth asteroids or main belt asteroids, Trojans of Mars or Jupiter. And also we are in, I put myself also in this asteroid comet continuum. We know that there are more and more common features between these bodies from their formation, also from the formation of the solar system. There are many constituents that are shared between these bodies, even if they are not completely equal. And include also the small and irregular satellites of main planets, which are also very similar in some sense to these asteroids we are studying. And in the general context, this has interest for planetary resources. More and more we hear about interest of going to asteroids to collect some material or to collect water for the future human exploration of space. In this context also we have heard already about the space situational awareness, where we are looking for mitigating a threatening asteroid. And so for that we need to know a bit better about the NEOs in general, and maybe on the target that would be on the curve to the Earth. We need to have a better description of this kind of bodies. And in general for the science, asteroids are really important, if not only interesting, to better understand the formation of the solar system and how we form then the planets, and also the dynamical evolution, the migration of the planets, and how this affects the asteroids. And these are also very good tracers to understand the formation and dynamical evolution of the solar system. So asteroids are also interesting, and we need to have knowledge of their physical properties in addition to the dynamical one. And physical is not only the surface or what kind of spectroscopy we could have, it's also to better know their mass and their internal structure that we need to know, or the mechanical behavior. If you want to do sample return, also we need to better understand how this body reacts to any kind of intrusion, or also how this reacts to rotation or to tides effects, etc. There have been already some space missions to small bodies, so asteroids, comets, and irregular satellites of Mars. About 20 targets, less than 20 targets have been visited. Here you have a sketch of among almost all of these bodies. The very biggest one, Stewarts and Vista, are not even represented here. They're much way bigger than these. And you can see there is a big variety of, well, first of missions. A few were really orbiting missions, but many of them are just a rendezvous mission. We just had a flyby to these bodies, taking a picture, and sometimes a bit more than just an image. And so we see a very big diversity also in sizes, of course. We have this big one, and then a very tiny one. Maybe you don't even see them from where you see it. And very diversity in the surface topography with craters for some, with very huge craters that are almost half of the size of these bodies. And with other with really regolith on smooth regolith, or with borders on the surface, representing very different kind of bodies. So diversity in size and surface, and also we can mention that no Trojan asteroid has been visited yet, no binary has been really visited yet. With an asteroid, of course, Ida and Dactyl have been visited as a binary, and Pluto and Charon have been visited too. But I would exclude them from the real list of small bodies. And what we know also from these bodies of the solar system comes mainly from the photometry observation, where we have we know about a bit less than 1 million asteroids been detected today, and one easy measurement is to look at the spin rate or the rotation period of these bodies, and you can see here this spin rate, spin period as a function of the size. So the big one is here, and you go to small ones that are less than a few meters large. There is 1 meter, and we see that first is this very well-known spin rate barrier, where we think any object that would spin faster than this limit, so these are spinning fast, would just disrupt. So this is something we understand as a cohesion of the self-gravitating body that explains this kind of spin barrier, and then we have a lot of diversity again of binary asteroids or tumbling asteroids. And when we go to small bodies, we can see that they can spin much faster, so they have a more cohesive strength. But even with low cohesive strength, as it is shown here, these are lines giving some cohesive strength you could find in snow, for instance. You can see that you can make them spin faster, but we don't know exactly how is the interior of these bodies. Are they just aggregates of blocks that are held together by gravity? Are there more monolithic bodies or differentiated bodies? Depending on the size, we can have something that is more connected resembling to a planet. So we don't know exactly how all these bodies are in the interior, and we don't know much about the masses of asteroids, except for the very big one like Cirrus Vista that have been visited. We well know the mass. For some others that have been visited, we have an indication of the mass. Here I could reproduce a figure giving you the total population of the number of objects for which we have the mass given with given precision. And as you can see, if you go to 50% precision, you have about 70 objects for which the mass is known, but if you go to 20%, it's less than 50. And of course, 100% is not really something that we are happy with. It's really a crude estimate. If you want to have a good mass estimation, we see that there are only a very few objects for which we have some mass determination or indication. And this can also vary with, going from the mass, we want to know also the density, and this can vary with the porosity of the body, and also maybe with the size of the body. They do not have all the same internal structure and density distribution given their size. And we know, for 10 years now, more also that from these bodies for which we have measured some masses, we have an indication of their porosity, and not just a monolithic big block where the density is completely uniform with the density of rock. We can see that sometimes the density is very low. For rocky asteroids, you can find a density of 1.2 instead of the double, the 2.5. So you have a porosity of about 50% for some objects, or even higher or lower. And here you have the effective diameter again, so the big one is US, and the other one are called the coherent bodies, more like the planet structure. And for the other one, we can think of having more fractured bodies with some voids, or going to very high porous with big voids or very low density material inside of these bodies, like Quinsac asteroids or comets that have more icy than volatiles. And the other one, very small bodies here that we see here for the NEO. And so the internal structure as a gravitational aggregate or rubber pies can have also different origin. Could it be due to post collision reaccumulation, or also from the York effect? The shape is also driven by this kind of fast spinning objects. And here is an example of one of the bodies that have been visited recently, Tokawa by the Hayabusa space probe. It also gave some sample return, and you can see again a very intricate shape with the borders on the surface. This is just an outcome of the granular behavior of this body, or from post collision or accumulation, but we know that this one is a very highly porous object, kind of rubber-hide example. So to get the mass, and even more than the mass, to have more insight on the internal structure, one way to do that, and we'll learn about other ways later on today, one way to use the planetary geodesy, that is, I will explain this in a moment, that here we are really thinking, and we started to have this idea after a call from the CISNOVA, connected the Coppins call connected to the Agnan mission. So we are thinking as a possible target of this binary asteroid Didymos with the Agnan mission, or other target possible is the Phobos with the NMX mission that is under development. But of course, our concept is to think of any mission accompanying a main mission to such a kind of a small body, and we want to derive the mass, the density, and the moment of the inertia and the gravity field of this body using the planetary geodesy. So some advantages of having a CubeSat is that we have a single instrument, and really we can dedicate a mission to this instrument, and we don't rely on the other PIs that are needing their own observing time. We need also, we can have some autonomy in the operation. We can get also closer to the surface for the planetary geodesy. The closer you can go to the surface, the better it is. Main mission will not take risks to go too close. With the CubeSat, we are allowed to take higher risks, and we can have this kind of proximity operation. Here we don't think of, for pragmatic reason, for not doing too complicated things, we don't think of having a direct link of radio science with the Earth, which would be more costly. This is the thing that I developed at KPL. We are relying on the mothercraft to do the links. And of course, we don't have an example yet of this kind of interplanetary radio science, so there is still some work to do. And we are looking at this kind of radio science and Doppler and echo ranging data to get a position of our core, combined with imaging, so the stellar astrometry gives us a position, and combined with imaging to get the shape and size and the rotation of the body. Possibly we could add also other kinds of complementary observation with Delta LIDAR, which might be difficult, but also an additional radio link with a lander, if ever, like the Mascot and Quinsac instruments, that will be very valuable to this kind of experiment. So BIRDY is our concept to small body exploration with a piggyback from the main mission. This is our general idea. Either in cruise or in proximity operation, and we really need the mothercraft as a relay, for focusing on that. So we need to have some autonomy on the CubeSat, because we don't want to put too much pressure on the mothercraft and the ground segments. And we can think of having one or two complementary CubeSats, and also eventually at the end of that, for the CubeSat to make it land on the surface and still emit radio waves. And in this concept, we are really focusing on three main aspects. One is the propulsion, the plasma thrusted propulsion, and having highly autonomous, highest possible autonomous orbit and navigation control, and on the radio science to get the precise orbit determination. So maybe I go briefly about the autonomous navigation, where the idea is to have a reference orbit and the measurement of background stars with foreground planetary objects to get the location in space and correct on board the orbit to follow the right track, and then you can, from this ground send again a new orbit, and having this kind of trajectories around the main body from the autonomous navigation on board. And for that also, for this different delta V, we need to apply. There is also the development of studies on the propulsion, and Gary Quinsac will give you a bit more details later on tomorrow, I think, on this student. So autonomous navigation, we have this as well for the attitude, then for the trajectory control in the loop, in flight attitude and orbit determination. Either in cruise or in proximity around a small body, And to learn more, I invite you to look at these talks of Boris Segret in Japan soon, and there will be another one for symposium later on. For the radio science, well, the basic idea is to have one-way or two-way links, radio link between the Earth and the spacecraft. Here we replace what we know about Earth and main spacecraft with our mothercraft and the CubeSat. And we try to get the position of our CubeSat and look at the perturbation he's having from the asteroid and measure the gravity field. And for that, you do typically a precise orbit determination. There are various codes for doing that and deriving the gravity field from the perturbation of the CubeSat. Some first estimates have shown that we can have a good estimate putting each band. Of course, we have to study more about the different bands available, but and different velocity. But we can have a good estimate of the mass, the first order mass of the body. Here it's Didymos and the width between the primary and the secondary. So the first estimate for this, and also we are looking at the stability of the possible orbits. And this is the work that has been done by a colleague from DLR, showing that you can have orbits more or less stable among these kind of bodies at a given distance. But we will focus, so we will work more on this in the coming months to see what orbits or what trajectory do we need to perform our radio science. And we have also looked at the different kind of orbits we can have around Phobos or Didymos, either as a quasi-satellite orbit or as a hovering orbit. So the assessment we still need to do, and we are working on that now. The radio scientists who look really at the link and the error budget of the radio link, depending on the different bands, depending on the one-way or two-way we can have, depending on the use of ultra-stable oscillator we can have on the mothercraft or we don't need. Whether we can have one or two CubeSats, of course it would be better to have two CubeSats to follow the gravity field, and also tuning all the external forces that can be rather large for this kind of CubeSat around a small body. And almost finished. So for the BIRDY-T, the first step is really to get the engineering model, looking at the propulsion and the autonomous navigation, and then we will also look at the radio science. But the first step is to have this engineering model to be developed between France and Taiwan. So thank you for your attention.